going to try to talk about some of the bread and butter of radio interferometry, about correlation, calibration, VLBI observations, and how we interpret some of the wavy lines that we see in radio maps of the night sky. So we may not all be here to do radio interferometry, but we are all here to find FRBs. We're here to understand what they are, what the sources of the bursts are, what are the bursts, what are the sources that make them, what are the transient and persistent counterparts at other wavelengths, their host galaxies, afterglows, things like that. We want to use FRBs as probes of the missing baryons, of the matter power spectrum and beyond. And in order to do this, we have realized as a field that we need to detect and pinpoint as many FRBs as possible. And so in this animation, I've shown the night sky. This is our playground, and we really want to mine this night sky for FRBs. So the first reason you should care about VLBI is because it is actually a technique which allows us to mine the sky extremely efficiently. And because I'm a member of CHIME, in this GIF, I've shown a picture of the night sky turning overhead. This is the northern hemisphere sky. You can see right in the middle of that red stripe, which is CHIME's primary beam. The North Pole stays fixed in this projection, and we scan the whole night sky once per day, trying to find FRBs. The reason why VLBI is a really powerful enabling technology is because traditional imaging interferometry makes it really hard to fill a night sky with beams to search for FRBs. So radio interferometry is a technique where you use multiple radio dishes together, not fast, not Arecibo, but something like the DSA 110, like ASCAP, or like CHIME. And you use these small receivers together in order to have a wider field of view to see more sky, to detect more FRBs. CHIME right now is one of the, has probably the largest field of view of any FRB detector. And you can see that it covers only a small part of the sky, something like 200 square degrees, or 1/50th of the night sky that you can see at any given time. However, even a small sliver of sky translates to a very high detection rate, and this is how VLBI enables it. It's a bit indirect. But traditional imaging interferometers make it really hard to fill a night sky with beams. The way you search for FRBs, if you take these two dishes, you take the electric field coming out of these two dishes, and then, hang on. Does this work? Around my neck. Oh, that's much better. Okay. Yeah, it's feeling a little awkward. Yeah, so the way that radio interferometry works is you hook up your dishes, you apply delays to one of your two dishes, and you phase and sum the voltages such that you're sensitive towards one part of the night sky. We call that patch of night sky a beam. I'm going to represent that with a rectangle in this animation. And if I sum the voltages, I can then downsample in time, downsample in frequency, and look for single pulses as a function of time. Since FRBs are occurring all over the night sky, it makes a lot of sense to try to search as much night sky as possible. We don't preferentially detect FRBs in one part of the sky or another, something that Alex just showed. So you want to not make one beam, but make many beams. In this example, I'm going to show just 7. So we're going to tile the sky with beams. Each beam is roughly the size of our point spread function. And in each of these beams, we're going to sum the voltages, square them, and search them for single pulses. Each of these searches involves a trial over dispersion measure. We need to align the time streams at each frequency with different time delays, such that we're sensitive to FRBs coming from different dispersion measures. And if you search over many dispersion measures, many possible FRB widths, and as a function of time, you might eventually, in one of your beams, detect an FRB. When the signal exceeds some certain threshold, you will say this is an FRB candidate. Hopefully, it's not radio frequency interference. You'll save it to disk, and then record voltages and move on and keep searching. CHIME does this every day of the year, 24 hours a day, except in the summer when it gets too hot in Montreal or in Penticton. So in this example of a traditional imaging interferometer, these telescopes are designed to have an exquisite PSF, the point spread function, which means that the PSF is really small. This makes it really hard to tile the whole night sky with beams. In contrast, CHIME is not an imaging interferometer. You can take your dishes and put them closer together. And what this translates to is that your beams get a lot bigger. And suddenly, with the same amount of compute power, you can cover a lot more night sky at once. And with this strategy, Chime still leads the field in terms of detection rate with GPUs and computing technology that is now approaching a decade old. Covering more sky means that each beam has much higher chance of seeing an FRB since there's a lot more universe in that direction. However, as we now know, in 2025, detecting an FRB is really just the start of the game. FRB science is quickly becoming a multi-wavelength field. Because once you detect an FRB, the next question is we want to study it and do things like follow it up, obtain redshifts, distance measurements, characterize it at multiple wavelengths. So you've seen some of the benefits of this compact array design, that you can have these big beams to detect lots and lots of FRBs, but now we sort of sacrifice angular resolution and we don't have an easy way to get it back. And what this means is that even within one of your detection beams, it's really hard to associate an FRB with any of the galaxies in this field, even with infinite optical information. So this is where VLBI comes in. It allows you to build these telescopes, these non-imaging interferometers with these funny big PSFs like Chime. And then you bring in VLBI to get the best of both worlds. No longer is it a question of do I use long baselines or short baselines, but you can have both. And you can sort of decouple this question of how accurate you want your interferometer to be from this question of how sensitive you want it to be. And that's what VLBI allows you to do. This allows us to pinpoint FRBs to host galaxies, obtain distance measurements, study the burst luminosities, study the local environments of these sources. And that's all possible with a combination of sensitivity and angular resolution over a wide field of view. VLBI and astrometry is a rising tide that lifts all boats. VLBI angular resolution allows us to take full advantage of space-based imaging, not limited by seeing from the ground. It allows us to zoom in on scales smaller than the scale of star formation, tens of parsecs in local galaxies. See Mawson's talk later about an exciting new FRB that we pinpointed using Chime and its VLBI outriggers. It also allows us to get the most out of our surveys. It allows us to make associations between FRBs and faint objects, both the luminous galaxies at high redshift, as well as the nearby low luminosity universe, which has already revealed a massive diversity of FRB formation channels and environments that these sources live in. VLBI has taught us things we would not know in other ways. For instance, as a result of these improved technical capabilities from the astrometric accuracy and precision of VLBI, we now know that not all FRBs have young progenitors. I once clung to a sort of this fairy tale in which all FRBs came from star-forming host galaxies. We now know that some of these are born in globular clusters or offset from star-forming regions, implying delayed formation channels relative to the time of the star formation. We also know from VLBI that a subset of repeating FRB sources are associated with flat spectrum, luminous radio emission, too compact to be star formation, too low luminosity to be AGNs, yet too luminous to be star formation. And that is potentially an important clue in the nature of what these sources are. I think I have more than, I'm a 30-minute talk, right? I'm 30, okay. That scared me for a second, okay. And so sources that are associated with persistent radio emission counterparts include 121102, R1, as well as FRB 2019-0520B, sometimes known as the R1 twin, because it also has a persistent radio source associated with it. We also know that FRBs exists in strange environments, such as in dwarf galaxies as down to 10 to the 8 in stellar mass, as well as massive ellipticals up to 10 to the 11, that's FRB 2024-0209A. And we also know from VLBI and studying and getting the most out of our space-based imaging that for a handful of sources, there are no optical companions down to typical O supergiant and O main sequence star luminosities. These are the two sources I have in mind are FRB 180916B. This is the periodic repeater, which was studied with the HST after EVN localization, as well as FRB 2025-0316A, as Mawson will talk about later. Some of my favorite FRBs are R3, 2018-0916B. You can remember this is the periodic one because the last two digits of the TNS name are 16B and it's 16-day periodic. I just realized this quite recently. My other favorite VLBI localized FRB is this FRB in M81, which was pinpointed to a globular cluster, also by the EVN team. Just a handful of these sources have already told us a wealth of information about VLBI. I think these are some of the first VLBI discovered single sources that are notable, including some of our favorites here. And in the right here, I've shown the recently localized FRB 2025-0316A, also pinpointed to an H2 region, but with a slight offset as we saw in the 16-day periodic source. So there are just a few gems for now. Each of these has taught us a lot about the FRB phenomenon, and there's lots more to come. The EVN is not the only game in the room. Chime FRB outriggers is online, doing well, pumping out FRBs. I think I've plotted for the first time the number of VLBI localizations as a function of time, and finally we're seeing sort of an uptick in this, enabled by the capability of doing VLBI on single pulses, something I worked on as a PhD student. Time FRB outriggers is doing really well. I will defer further talk of that array to Matthias and Ziggy later. But this is just the beginning for VLBI and FRBs because a slew of new instruments is coming online, going to use compact arrays and VLBI in order to pinpoint these sources, understand their origins, not in hundreds or thousands, but at the scale of 10,000 or more. And these are chord, burst, and other future efforts, such as charts in the Southern Hemisphere. So now I hope I've motivated why angular resolution is important, why I think VLBI is going to be the future of our field. I think the existence of chord, burst, charts sort of point to the final FRB experiment, which is compact arrays, VLBI for angular resolution, and the field is sort of converging on this design, meaning VLBI is going to be really important. So let's talk about it a little bit more. Now I want to spend the remainder of my talk sort of going into detail about how VLBI works. At its core, VLBI is a question about correlation. How do you line up the crests and troughs of your electric field signal entering your radio dishes? In this schematic, I've depicted radio waves in red going into my dishes. And if I correlate these waves as a function of time, then what I see is that the radio waves are positively correlated. If there's no delay, then the phase should be, these waves are aligned in phase. And what I mean is that if I multiply the top curve by the bottom curve and I sum over time, I get a positive number. However, if I look at a different part of the sky, I get a different number because of a different geometric delay towards my source. In this case, the waves are anti-aligned, and you can see that if I multiply them together and sum them as a function of time, I get a negative number. Sometimes it's a little hard to interpret when your signal can be positive or negative. So something that we like to do in radio interferometry is break up the electric field signal as a function of time. It's really convenient to do this to make our data volumes more manageable. So you don't need to correlate this entire the top wave against the bottom wave for all time. You just do it chunk by chunk, and this allows you to parallelize things nicely. And in this example, each chunk is anti-correlated with the bottom chunk. You get negative correlations for each of these three chunks. Then you can aggregate together these integrations or sub-integrations into a measurement of the visibility or the correlation between the top antenna and the bottom antenna. You get a negative number. That's okay. It's an overall phase offset. So this is what's happening for a source at the North Pole. Let's consider now what happens when we go off axis a bit. Let's say the North Pole is a special place in the sky because it's fixed as a function of time. If I have two antennas in the Northern Hemisphere, they can always see the North Pole, and the North Pole doesn't change in the Earth's frame. So the delays towards the North Pole are static as a function of time. So if I have two identical antennas, I get positive correlations in all three segments, all three of my sub-integrations. I sum them together, I get a positive correlation. However, the story gets a little more complicated for sources not at the North Pole. You can think of now a source at the horizon. There's going to be a different delay towards each of my antennas. And what's going to happen is that the waves are going to be shifted slightly as a function of time and where your antennas are. In this example, the waves on the left remain correlated, the ones in the middle are not really correlated at all, and the ones on the right are anti-correlated. And the problem is if I stack these measurements, I get something that's 0. It's sort of obvious that I've misaligned these waves as a function of time. I've also colored some of them differently. And what this refers to is the fact that there's actually a net radial velocity for sources off from the phase center here, the North Pole. In other words, since my Earth is rotating, if I see a spectral line at the horizon, I will see it at a slightly different redshift or blue shift in my front antenna versus my back antenna because Earth is rotating. Now, this is a problem because if we just sum the waves, we would get no sensitivity. We would not get a signal, even if the source were extremely bright. To fix this problem is a well-studied thing in radio interferometry. This is the job of a piece of software or a piece of hardware that we call the correlator. It breaks the data into chunks, and it figures out how big the chunks are. And then you tell the correlator what position you want to be sensitive to. And it calculates the delays towards that position using a highly accurate and precise delay model. It aligns the waves not just by changing their position as a function of time, but also applying a Doppler shift, a red shift or a blue shift to each segment individually, such that they are the same color again towards that phase center. That correlator then tells you, okay, I've maximized my sensitivity towards this point in the sky. Now I'm going to repeat the correlation process. I'm going to multiply the two waves together as a function of time, sum, and then I get my signal back, even for sources not at the North Pole, sources that are potentially rotating in the sky that are not static as a function of time. There's a couple of codes used for VLBI correlation. Probably the most well-known is diffx, written by Adam Deller, who I know is on the call. There's also SFXC, written by Ard Kempema at Astron. LOFAR uses something else, and because of the time, we wrote our own piece of code. I wrote this piece of code along with Shio and Andrew. We call this PyFX, and we have now used that piece of code. It's all written in Python to localize hundreds of FRBs using VLBI. So now that we've talked about VLBI correlation, I want to now talk briefly about what happens afterwards. There's also calibration required. Your antennas are not all designed the same. They have different cable lengths, different delays and phases. So at bare minimum, you need to do delay calibration, you need to do phase calibration and ionosphere corrections. How you solve for these parameters? You need a bright network of compact sources in the sky, which have well-defined positions for you to do VLBI. Fortunately for us, the folks at the VLBA are really good at doing this. There is now a radio fundamental catalog of over 20,000 sources over the whole night sky, maybe 1 every 2 square degrees, with positions at 1.5, 3, 5, and 8 gigahertz. Leonid Petrov is putting out a new catalog every couple of months, and so if you have an old version of the VLBA calibrator catalog, you should be loaded every now and then. A subset of these 20,000 sources actually define what it means to have certain RA and DEC coordinates. A different subset of these sources also have optical counterparts, and those let us tie the radio frame, which define the RA and DEC coordinate system, to Gaia. And so what this means is that in the optical wavelengths, with a couple of calibration stars from Gaia, you can use this connection to the ICRF in order to achieve a local frame tie that's on the order of 10 milliarcseconds or better in many cases using that the Gaia astrometry. So this is what happens at 1.5 gigahertz and above. At lower frequencies, the story is a little more complicated because it's just not as well studied in terms of VLBI. There's not a lot of papers on this. Some of the early ones are by Clark, 1975. Also some observations with radio Astron, and also Emil Leung surveying the sky at low frequencies. This field sort of hit a wall in 2009. Most data from the VLBA at 92 centimeters, I actually learned is completely public, but unpublished because it's just so hard to observe there. And so what we've had to do in order to look at FRBs with VLBI with chime is to make our own calibrator catalog. There's no low frequency catalog which existed for doing astrometric VLBI at the frequencies that are most interesting for FRBs. And I define this to be roughly a gigahertz, maybe a bit lower, going all the way down to 300, 400 megahertz. Existing surveys from LOFAR were either too low resolution or they did not have an astrometric tie. And so it took chime outriggers coming online to really fill in the gap in terms of calibrator coverage, as I've shown in this on the right, where I have angular resolution or longest baseline on the x-axis, and frequency on the y-axis. So chime outriggers fills an important part of that parameter space. And we're hoping that chime outriggers will also pave the way for the next generation of FRB detection experiments by providing a low-frequency all-sky survey of calibrators with astrometric availability, so that regardless of where you detect your FRBs, you will be able to find a calibrator and reference that FRB to the ICRF. So I mentioned earlier that once you have a calibrator, you want to perform calibration. There's a couple of steps: delay, phase, ionosphere calibration. The big one is delay calibration. You typically use the brightest sources in the sky for this, bright and compact, and hopefully with well-determined or defining positions in the ICRF. Delays mean that your waves are not aligned as a function of frequency. You can bring those back into alignment. And after delay calibration, you're typically okay for astrometry unless you want to image. If you want to image, you also have to take care of an overall phase between your two antennas. That's sort of a small effect I've shown on the right. I've plotted in the top panel an image, a 1D image of the sky with flux on the y-axis and delay or sky angle on the x-axis. And in the bottom, I'm plotted the overall phase. You can see that applying a small phase shift makes a very small difference to the PSF, but it does subtly change the position and the relative intensities of the side lobes, which is really important for imaging. After delay and phase calibration, we sometimes have to do ionospheric calibration. What I've learned in VLBI is we don't really talk about the ionosphere that much, but it actually turns out it's really important at low frequencies. And the reason is that at low frequencies, there's not only a geometric delay, but there's also an ionospheric delay, which due to the presence of electrons gives you a lambda square delay. It's pretty hard to tell what the difference is in the phases as a function of frequency if I have a narrow bandwidth. What's nice about chime and about future FRB experiments is that with a wide fractional bandwidth, it's possible to simultaneously fit for your 1 over frequency as well as your proportional to frequency delays here. Oh, right, I'll let this play again because I think it's a cool animation. So here's the thing. There's a source moving around. I want you to see what happens to the phase as a function of frequency. It's sort of linear. You can't really distinguish that quadratic part of the phase. But when I uncover the full bandwidth that we have, we can sort of see by eye exactly how much ionosphere is present. So here again, there's a source changing position in the sky. There's also an ionospheric correction. If you're not working at low frequencies, if you're working at L band or above, typically what you do is you apply a ionospheric model, which is measured with GPS. However, this only takes into account fluctuations of the ionosphere on large scales, not small traveling ionospheric disturbances, which are better to self-calibrate out using observations of nearby calibrators. So now we've talked about correlation, calibration, why we should care. Let's actually do some VLBI. For an example, here is a target on the sky, a phase center, hopefully close to the target. We mentioned earlier that if you are too far away from the phase center, you lose sensitivity. So in practice, you want to be as close as possible to the phase center before you start your VLBI session. This means having a preliminary localization of your FRB or some archival position that you point at. Arc minutes is good. More than that, degrees, that's worse. Radio telescopes are diffraction limited, so I won't show you what the true sky is. I'll show you what the radio telescope sees, which is a blob of size lambda over d. And I mentioned previously that this gives you constructive interference. If you move off axis, it gives you destructive interference when your waves are off by 180 degrees in phase. If you keep going off to the side, then you get positive correlations, constructive interference yet again. This happens on the other side of the sky as well. And this oscillatory pattern, the interferometer response, looks like a sine wave across the sky. And in principle, this sine wave goes off to infinity. However, in practice, this is limited not just by the correlator field of view, but also a contribution from the primary beam if you go way off to the sides. Typically, your correlator field of view is smaller than your dishes for a well-designed telescope, giving you some total sensitivity. So you want to make sure you're pointing approximately correctly, and you also want to make sure that your correlator is pointing close to where you think your target is going to be. And so to close out this talk, I want to now observe a source and sort of lay the foundation for the rest of this conference, which will talk about FRB observations. Let's talk about observing a point source versus an extended source. For instance, a point source might be an FRB, or it might be one of these compact persistent radio sources. An extended source might be star formation in its host galaxy. And so what I do to see what my interferometer will see is I put on the interferometer response, I overlay it on top of my source function, which is a positive function over the whole sky. And I now integrate over the whole sky, or in practice, over the size of my primary beam. I see positive contributions and negative contribution. These two functions get multiplied together. And since the source is positive, it is in a positive part of my interferometer response, I get a positive contribution to the visibility on short baselines from that source. The same thing happens on long baselines. There's a different Fourier mode, a more oscillatory one that goes across the sky. And because my point source fits in one of these positive lobes, it gives me a positive contribution. For more extended emission, we need to go to shorter baselines. And so at short baselines, you can sort of well match the interferometer response to the size of the object you want to study. You get positive and negative contributions summed across the whole sky. The cloud here will give you a positive contribution. However, one subtlety in radio wavelengths that I want to stress is that if you use long baselines to observe extended emission, you actually don't see it at all, because there are positive and negative contributions from the interferometer response when superimposed on top of the source that you're looking at. Another way of saying this same thing is as follows. Here I plotted the true flux as a function of sky position. What the interferometer sees if you have many long baselines looks a little more like this, where the contribution from the extended emission is suppressed. If you have fewer long baselines, just one or two baselines, then what you see is something a little more oscillatory. Oh, by the way, that's the beam shape, or the PSF. And the beam shape gets a little more oscillatory if you have worse UV coverage, worse frequency coverage, or both. We see this in the literature. Here is an image of, I think, the persistent radio source from 121102. You can see the beam shape specified in the lower right corner. And you can see that, as predicted, the flux goes negative in some places, which is sort of weird in radio. Doesn't happen to other wavelengths. But it's really just a result of the PSF being oscillatory as a function of position on the sky. Right now, the field is also building towards this regime where you have oscillatory fringe patterns. Here are two examples where that's relevant. Tomas and I and Pranav localized this, the very first VLBI localized non-repeating FRB. This paper was finally published in 2024. You see an oscillatory fringe pattern as a function of REN deck. There's just two baselines here. Also, we see the same thing happening in Dante's paper, Hewitt, in 2025, where the localization ellipses increase in size from something like milliarcseconds to hundreds of milliarcseconds or tens. Turns out this is good enough for most FRB purposes. And so at that point, I'll just say that we sort of made it both to the end of this talk and in terms of realizing the dream of FRB VLBI over the whole sky for FRBs. VLBI, in conclusion, it lifts all boats. It enables us to use design better FRB telescopes optimized for FRB detection, freeing us from the constraints of localization, allows us to do space-based follow-up. It opens up the possibility of diverse environment studies and allows us to characterize multi-wavelength companions to FRBs. And before I go, I just want to say that CHIME FRB Outriggers is hopefully the first of many telescopes which will use VLBI to localize these sources. And I just want to give a shout out to some of my colleagues who will be giving more extended talks on CHIME and this Outrigger program. I want to end with a picture of my new kitten. Thank you.
Thank you very much for that nice talk, Dr. Calvin. It's I mean, like a lot of things, gives a good introduction for all newcomers. All right, short question. Yeah.
Oh. I'm kind of constrained here, so I'm not gonna even try to throw it.
Thanks. My question is very, very basic. So you said that you hope that CHIME will provide like a catalog of calibrators for low frequencies, which hasn't been done before, but obviously CHIME can't see the whole sky. So I was wondering if you knew if there was any plans to, by any facility, maybe someone else knows the answer to this, to have a Southern Hemisphere equivalent.
Yeah, it's a great question. I guess the question is, I feel like the Australians probably have a better answer to this than myself. The VLBA calibrator catalog seems to be working in the Northern Hemisphere. There's no reason why it shouldn't work in the South as well, although the source density is a bit lower there. So I suspect if you build something like charts and observe in the South, you'll just see the calibrators.
Great, thanks.
I should also mention that we actually have published one of these calibrator catalogs already. This is Leung's paper.
Liam, go ahead.
Hey, Calvin, that was a great talk. I loved all the visualization. Okay, so with long wavelength VLBI and just a few baselines, you don't quite get to the diffraction limit because the ionosphere, lack of UV coverage, calibration, other systematics, seems like you get to about 100 milliarcseconds, which is obviously incredible, but for an array like ASCAP or DSA 110 or the Chime core, you go significantly below the diffraction limit by a factor of about the signal to noise. So DSA 2000, for example, will have a 2 or 3 arcsecond PSF, and it'll get to 100 milliarcseconds localization for a 20 sigma burst. So my question for you is, how do we optimize this trade-off for future arrays? Is there a middle ground we should be considering where you don't actually need the international VLBI networks? Or am I missing something and actually Chord and Chime VLBI really have landed at like a global minimum?
Yeah, it's a great question. The question of how much you super resolve your PSF is sort of thorny, as it's not always clear how much that happens as a function of signal to noise on different baselines. Right now, what we do in Chime outriggers, which is sort of panned out, is that we're not super resolving the PSF. We are inflating the localization ellipses relative to diffraction by a factor of 2 or 3, although it depends on things like the noise and wavelength coverage. What I will say is that that's actually the correct choice, not because of ionosphere considerations, but because we see RFI substantially increases the scatter in our pulsar localizations and continuum source localizations as a function. RFI scatters the overall positions more than ionosphere does. And so that's why we do what we do. So I think this is sort of the right way to go to completely decouple the design of the core stations from long baseline stations. I hope that answered your question, Leung. Okay.
Right. So let's thank the speaker again.